The Arduino only has a relatively small number of digital outputs. While there are enough of them to get us through most of the examples in this course, in many real-life projects they will be not enough. Take for example the case of a gadget that contains a character LCD screen, a couple of status LEDs, a couple of buttons and a couple of sensors and a Wi-Fi breakout. You'll need 2 pins for the screen using the serial to parallel adapter, 2 for the LEDs, 2 for the buttons, at least 2 for the sensors and 6 for the Wi-Fi breakout. That more or less exhausts the available ports. Sooner or later, you need a way to multiply the available inputs and outputs so that you can connect a larger variety of peripherals. In this lecture, I'll show you how to use shift registers to multiply the available digital outputs. In a later lecture, I will also introduce you to I2C-driven port expanders. These technologies make it possible to design ever larger and realistic gadgets using a single low-cost microcontroller. In both cases, shift registers and I2C-driven port expanders allow you to reduce the amount of Arduino pins tied up for a particular peripheral and delegate the control of those peripherals to external controllers. Before getting into it, I should highlight that more available pins do not automatically guarantee that you will be able to create larger gadgets. Once the input-output port availability is dealt with, the next potential showstopper is memory. The Arduino Uno's microcontroller only has 32 kilobytes of flash memory. With that amount of memory, it becomes difficult to create sketches that match the ever-growing hardware they are supposed to drive. Also, in a later lecture, I will talk about ways to manage and optimize memory use. Think of a shift register as a single byte memory. Each of the bits in this memory is connected to the outside world via a pin on the package of the chip that contains the memory. You use a single data pin from the Arduino to write each bit, one at a time. Because each bit is written individually and all bits can be read all at once, we say that shift registers are devices that support serial in and parallel out. To support the serial transfer of bits from the Arduino to the shift register chip, we need a second pin to provide a clock signal. Every time the clock ticks, one bit is transmitted from the Arduino to the shift register. Once the new bit is received by the shift register, all existing bits are shifted by one bit to make room for the new one. This shifting process is what gave the name shift register to this device. Here's a graphical way to look at this process. Let's say that we'd like to store the byte 11001101 in the shift register represented by this table. At start, the shift register has an undeterminable state, so I'll represent this with question marks. So this is step 0. In step 1, we'll take the least significant bit, which is the first from the right, it's a number 1 in this case, wait for the clock to tick and shift it in the register. We could have chosen to start with the most significant bit just the same. And this is the result of the contents of the shift register after step 1 is completed. And you can see that number 1 has been inserted into the shift register on its leftmost box. Notice the gray box at the end of the register. This is an additional overflow bit memory that stores the bit that was shifted into it from the bit on its left. We will be using this overflow bit in the second demo in this series of lectures when we create a circuit that uses 2 shift registers connected in series. In step 2, we'll take the next least significant bit, which is the second from the right, which is a 0 in this case, wait for the clock to tick and shift it in the register. Notice that the original first most significant bit, the 1, is grayed out to show that it's already been transmitted to the register. we now also have the first bit that shifts out of the overflow bit and is lost. So here's the outcome of step 2. In step 3, the same process continues. The clock ticks, the next bit in the sequence, which is a 1 in this case, is sent to the shift register, and all existing bits in the register are shifted 1 position to the right to make room for the new bit. So here's the outcome of the 3rd step, and you can see that the first 3 bits have been inserted on the left side of the green highlighted set of boxes. I will speed up the rest of the sequence. This is step 4, step 5, step 6, step 7, and finally step 8. The complete byte now has been shifted into the shift register. You can send single bits to the register. It's not necessary to do so for a whole byte, although most libraries make the latter easier than the former. Another way to think about the way that this register operates is FIFO, which stands for first bit in is first bit out. So I hope you have now a solid understanding of this process. It will make it easy to understand what is happening with the next 2 demonstrations that follow. In the first of these 2 demonstrations, I will show you how to use a shift register to control an array of 8 LEDs using a single shift register. And then in the second demonstration, I will show you how to use 2 shift registers to control 16 LEDs without increasing the number of pins that we have dedicated to the control of these 16 bits from the Arduino. So let's go ahead and have a look at the first demonstration next. Thanks for watching. If you'd like to learn more, check out my Arduino Step-by-Step Getting Started and Arduino Step-by-Step Getting Serious courses on the Tech Explorations School. There, I help you develop basic and more advanced Arduino skills, including how to write your own programs, how to use all sorts of sensors and actuators, and how to create your own gadgets. You may also be interested in my project courses, where you get deep into the development of wheeled robots, remote-controlled cars, and drones. Please use the coupon code in the description below this video to get a YouTube exclusive discount to my courses. See you there!